hand over to Mike Eastwood, who is the first speaker, killing tensors on complex projective spaces.
Yeah, so I mean, there's some twistor theory here, but I'm not going to, start with that or anything like that. So I have to tell you what, killing tensors are, and you probably already know what complex projective space is. But there's some history here, and these are the people who are involved some time ago, like maybe 20 years ago, 10 years ago, 3 years ago, and so on, a couple of weeks ago. But generally speaking, lots of these constructions and so on are due to the influence, at least for me, of Roger Penrose. Okay, so I should tell you what these things are. First of all, rather than killing tensors, let me either tell you or remind you what a killing field is. So there's a background smooth manifold. All of this talk is, although it's on complex projective space, that all of the constructions and so on are local constructions. So let me just write things out as if they're in local coordinates. So here, for example, is a metric. So either that's an expression for the metric in local coordinates, a Riemannian metric, let's say, or it's some abstract index notation, right, due to Roger Penrose. If you've got a metric, this is the Levi-Civita connection which goes along with it. And again, this is decorated with a little index to indicate that you're ending up with a one form with values in something or other. Start with a tensor and hit it with one of these things, you get a one form. And in particular, you can look at a smooth vector field on this manifold. There's some consistency here. So if I've got indices up like that, that means it's a vector field. If I have indices down, it means it's a one form or it's a tensor with covariant indices, like the metric. Okay, so I mean, yell if you want to object, if you want any more information, but I guess lots of this is familiar to everybody. But of course, if you have a metric, you need not distinguish between vector fields and one forms. And here, again, using this index notation and the abstract and the Einstein summation convention, this is the relationship between vector fields and one forms. And now, here's a formula which relates these various things. So what happens if you look at the Lie derivative of the metric along a vector field? Okay, then it turns out that if you use the Levi-Civita connection, right, so that's the metric connection, then the Lie derivative is easily expressed in terms of the connection applied to the one form rather than the vector field. Okay, so I'm using all of this in a sort of canonical way. Vector field becomes one form. You've got this connection there, and that is a genuine formula for the Lie derivative. Okay, and therefore, if you have a setup like this, and you have a symmetry of your manifold, in other words, an infinitesimal isometry of your manifold, then this thing here in the yellow box should vanish, right? And that's the definition of a killing field. So a killing field is a field such that if you lower the index, you take the Levi-Civita connection of that, and then take its symmetric parts, right? So another small piece of information here, also due to Roger Penrose. If you put round brackets around a couple of indices like that, it means take the symmetric part of that matrix, if you like. So it's a half of what's in the yellow box there. Anyway, a killing field is such that is one of these things. So that's an infinitesimal symmetry of your manifold. Right, so let's run through some examples that everybody knows. Like, what happens if you ask what are the killing fields on Euclidean space? You're expecting translations and rotations, and sure enough, if you try and solve this differential equation, this is a very tight system of partial differential equations, you find that this is the general solution.
So it's infinitesimal rotation.
These are all infinitesimal. Everything's infinitesimal. Yeah, thanks, Claude. Right, so infinitesimal translation, that's the first thing. And here you have, things like x dy minus y dx. So generally speaking, some skew matrix giving you infinitesimal rotations. This is what the general vector field looks like, general killing field in Euclidean space. And if you like, you can put these things together to get some sort of more exotic object, like a Lie algebra. Okay, if you do it on the sphere, for example, then you can express all this in terms of the ambient coordinates. So this is x with an alpha index, which means that you're looking at coordinates on the ambient space in which your sphere is embedded. And then you find that this is the general solution of those equations on the sphere. Okay, so I'm writing down a field which makes sense off the sphere as well, but this is something when you restrict it to the sphere, this is the general solution of these equations. Okay, so this is a skew n plus 1 by n plus 1 matrix. Okay, if you like, again, you can put these together and get yourself a Lie algebra. And one thing to notice at this point is that the dimension of this just space of solutions is actually the same either on Euclidean space or on the sphere. And that's not an accident, right? There's something going on here which is significant. All right, so that's killing fields. Now what about killing tensors? So killing tensors, at least just to define them, what you do is you take something with k symmetric indices like that. So if k was 1, it would be a 1 form, and otherwise it's a symmetric tensor. And the equation for killing tensor is simply you take the, you've got the situation from the previous slide, you've got a metric, a connection, and so on. You take the connection, apply it to this, and take the symmetric part and ask that it be 0. So if k is 1, this is a killing field. Right, and otherwise it's a killing tensor. And at this point, we could have a little digression of, why it is that killing tensors are important and so on. But that would be too much of a digression. I'm not going to do that. It's just, this is the definition. Okay, something to do with conserved quantities and so on and so forth. Right, now amazingly, you can solve this equation. First of all, this is a very strong equation. I mentioned that already for the killing fields. But this one also has a finite dimensional space of solutions. So it's overdetermined. It's a very strong set of equations. Here's the geometry of what's going on the sphere. So here's a sphere, and I've drawn it as a 2-sphere, but it could be an n-sphere. That's a geodesic running around the sphere. It obviously has something to do with the metric. You put a light source at the center of the sphere, and you take central projection from the sphere down onto a plane. And the claim is that if you set this upright, then these equations behave well with respect to this central projection. So they have some invariance. So strictly speaking, they're projectively invariant, these equations, if you set it upright. Okay, so in other words, what you can do is you can envisage these equations just in flat space and put flat space inside of the sphere according to this diagram. And you end up solving these equations in flat space. It's the same as solving them on the sphere. And because of this geometry here, the symmetry group is a little bit bigger, well, quite a lot bigger than what you would expect. So what you would expect is that the symmetry group for the sphere would be SON plus 1, right? Isometries of the sphere. But actually, the symmetry group is a lot bigger, right? So this is the symmetry group which respects these equations. So the conclusion is that killing tensors on the sphere are actually, well, first of all, I'll explain a little bit more about this in a moment. It's a finite dimensional space, finite dimensional vector space. This group is acting, right? So it's a representation of this group. and actually it turns out to be irreducible, right? So it's a bit of a surprise that you can, say explicitly what's happening in this particular case, and and now there's some hieroglyphics involved. So the irreducible representations of this, which is a simple Lie group, are described by annotating some Dynkin diagram in some way, and either you know what's going on here or you don't, and I'm not going to explain if you don't, right? So otherwise, this is an irreducible representation of this group, and this is can be identified with the space of Killing tensors.
Can I ask you a question, please?
Yeah.
When you say symmetry group, what do you refer to? How do you combine the Killing tensors? I mean, for Killing vectors, I suppose you have the bracket.
Oh no, I'm not. Okay, I'm not taking a Killing a Killing tensor and another Killing tensor, putting them together. You can of course put a Killing tensor together with a Killing vector, take the Lie bracket, and you get another Killing tensor. But that would just be saying that this Killing tensor equation is invariant under rotations.
So
but it's better. This is a bit of a surprise, right? It's a bit of a surprise that there's a bigger group which is involved.
So in the special case of Killing vector fields, it's, I think, important to notice here that it's not the Lie algebra structure.
Yep.
So that the bracket involves raising an index.
Yeah.
So,
let's go.
so you get the same vector space, but it's actually, they have different Lie algebra structures.
Right, so here in flat space and on the sphere, these are both Lie algebras. They just happen to have the same dimension. Right, so I'm not saying I really only care about this as a vector, as a finite dimensional vector space, and for example, what its dimension is. Right, in the sphere and flat space, they're the same, and that happens for Killing tensors as well. Right, so just so you, okay, so I'm not, but I'm just saying that there's a way of setting it up so that this equation here intertwines well with this central projection. Oh, the other thing is that if you look at the so this central projection, what's really going on, perhaps, is that this central projection is taking geodesics on the sphere to straight lines in the plane. Right, and that really characterizes what's going on here. And if you look at the automorphisms of the plane, which takes straight lines to straight lines, or you look at automorphisms of the sphere, which takes straight lines to straight lines, then these groups act on the space of Killing tensors. Right? So I'm not going. This is quite complicated, so I'm not going to explain this in detail. It takes a bit of getting around. But in particular, the space of say smooth transformations of the sphere to the sphere, which takes geodesics to the geodesics. It's this group, right, which is bigger than the isometry group, right, because you're taking unparameterized geodesics to unparameterized geodesics. Okay, okay, I prefer not to say any more. Right, so but in particular, you can read off what the dimension of this space is. Here it is, right? So this is a formula involving n, which is the dimension of your sphere, and k, which is how many indices this thing has on it. Okay, so this was realized, I don't know, in the 1980s sometime. Several people realized this. This formula goes by various different names. But the fact that it's actually a representation of this bigger group is a really good way of establishing this formula. This is a very, very standard formula for what the dimension of an irreducible representation of this group is. Right, so there's all sorts of Lie theory just lurking in the background.
So in terms of this paradox that you don't get the same Lie algebra for sphere and Euclidean space, it's important that you're really looking at the space of one forms that satisfy and not vector. So you have to think of them as vector fields in order to take them.
So as Claude's saying, in particular, in order for this equation, I've started sort of luring you towards this viewpoint, whereby you shouldn't think of these things as, even when k is 1, you really shouldn't think of these things as vector fields. You should really think of them as one-forms. And you should think of these things as tensors with downstairs indices. Okay, right. Please object. Thank you for objecting. Right. Okay, now let me just try and tell you why it is that these spaces are finite dimensional. Why is that? Right? So there's some general theory which just says that they are, right? But here's a much more explicit way of figuring out that this is true. So here's the equation of killing fields, right? We're going back to the case of one index. Okay, and I'm just going to maneuver these tensors a little bit in a way which shows you that the space of, even locally, the space of solutions of this equation is going to be finite dimensional, and even tell you what its dimension is, roughly speaking. Right, so to say that this symmetric part is 0 is to say that when you differentiate this thing, you get something which is skew. Okay, so this implication here, this equivalence here, nothing is happening, right? The wheels are spinning. It's just that that's another way of saying that the symmetric part is 0. Okay, now, and now you just differentiate this thing one more time. So what I'm doing here is a process called, informally at least, called prolongation. So I'll just say it in words. If you've got a system of equations, system of partial differential equations, and you want to investigate that system, it might even be nonlinear or whatever, one of the things that you can do is you can invent names for the derivatives of your basic fields that you don't know. And that's what I'm doing here. So if, for example, all of the derivatives of sigmas was 0, like the whole collection of derivatives, then in flat space, sigma would just be constant. But here, it's not that you know that all of the derivatives are 0. You know that most of the derivatives are 0. The symmetric part is 0. The skew part is left up in the air for the moment. So what you should do is say, well, okay, we're going to give names to the skew part, call it mu, and then see if there's any restrictions on the derivative of the things that you've introduced. All right, this is prolongation. Again, informally. All right, so let's look at the derivative of these mu gadgets and just think about what's happening in flat space. So in flat space, if you look at that thing, that tensor with 3 indices, it's skew in its last 2 indices, just because mu was. But it's also symmetric in its first 2 indices, a and b, because it's actually just the second derivative, right? So it's just the second derivative of sigma, it's just the Hessian of sigma, in flat space. So now, if you've got a tensor with 3 indices on it, and again, there's much more going on here. If you've got a tensor with 3 indices on it, which is symmetric in one pair and skew in the other pair, it's 0. That's the sort of basic algebraic ingredient in the construction of the Levi-Civita connection. And that's not a coincidence. Okay, so there's lots more to say. So this derivative is 0. If you just repeat this in curved space rather than in flat space, you don't get the derivative of mu to be 0, but you do get a formula for it in terms of sigma and curvature. Okay, so what you find is that you get what can be assembled into the following gadget, which is a connection. So you have a new field which comprises something which is a 1 form together with a 2 form, sigma and mu, such that the equations are that, well, to say that mu is the derivative of sigma is to say that the first line of this, what I'm now writing as a prolongate, as a connection, is 0. And then the second line is what you get if you just repeat this argument in curved space. You get that the derivative of mu, rather than being 0, is equal to some curvature on sigma. Okay, so this is a standard maneuver, and now there's some connection with twistor theory from a long time ago, because another equation which is overdetermined like this is what's called the twistor equation on spinors in 4 dimensions. And if you do this process for the twistor equation, you get a connection which has a name. It's called the local twistor transport. Okay, but laying that on one side, one thing you can do is just read off that the dimension of the killing fields in complete generality and locally, in complete generality on any Riemannian manifold, is bounded by the rank of this bundle. And this bundle has rank n plus 1 over 2. A familiar number which appeared on the very first slide. If you do it for killing 2 tensors, again there's some hieroglyphics involved. If you do it for 2 tensors, then you just do this exact same procedure, but it lasts a little bit longer before it closes up. Right? So what you get is you get a sigma which has symmetric indices, and this is some sort of hieroglyphics for saying that sigma with 2 indices and symmetric, and then you get some sort of symmetry on its derivative and so on, and you get a connection on this bundle instead, which in detail is actually quite a mess. But nevertheless, you can read off that the dimension is bounded by whatever the dimension of this bundle is. So the dimension of the killing fields, killing 2 tensors, in general, complete generality, is finite. It's finitely determined, and this is a maximum for the dimension. And it's attained on the sphere.
It might be worth pointing out in the case of killing fields that the equation that you get out restricts to a GDZ as exactly the Jacobi equation for the joining vector field. But for higher order things, you have. Yeah, it's not so easy to understand. It doesn't easily
that's
reduce
right.
to a single.
And that's the real distinction between killing fields, which have this nice geometric interpretation, and killing tensors, which have somewhat of a geometric interpretation, especially along geodesics. But, okay. Yeah. Okay. Never mind. So what about killing 2 tensors on the unit n sphere? So what I'm going to do is sort of lead you towards what I'd really like to know, which is actually what are the killing tensors on quaternionic projective space. That would be something I'd like to know. Okay, but I can tell you what killing tensors on the unit n sphere are like, and that's from the 1980s. This is. Killing 2 tensors on, or killing tensors in general on complex projective space, that's relatively recent. And then on quaternionic projective space, I don't really know what's going on. So part of this talk, by the way, is a plea for help. All right? So if anybody can figure out, I can present some things which I know to be true because you can just test these things with Maple and so on, but I don't know why they're true, and I don't have a proof or anything. We'll come to that. So, okay, so pay attention. There are puzzles for the audience all the time. Okay. Right, so, you know these mysterious formula about the bound on the dimension of the killing tensors? This mysterious formula, you can say it all in terms of these other things which are called Young tableau. Okay, so there's you know, once you're into representation and theory and so on, there's another notation for this representation, and this is how you work out its dimension. You work out its dimension by feeding various numbers into these boxes. And this is where this n plus 1 squared n plus 2 over 12 comes from, more abstractly. Okay, that was the number that we got on the previous slide for an upper bound on the number of, on the dimension of the space of killing 2 tensors. And it's attained on the unit sphere. So this is how many there are on the unit sphere. Now, of course, one thing that you can do is sort of revert to a more primitive viewpoint and look at the killing tensors under the isometry group rather than this more exotic projective symmetry group. Okay, so let's do that. And here is a way of investigating the killing tensors on the sphere, killing two tensors on the sphere. This particular representation, again, there's some hieroglyphics involved, but it breaks up into three irreducible parts. And then there's a geometric interpretation of this, that there are three types of killing tensors on the sphere.
Here you're using the metric too.
And here I'm using the metric. Oh, yeah. Yes, yeah, yes, right. So, yeah. So although at the beginning of the talk you start with a metric, and then you get this connection and so on, and you can throw away the metric. But now I'm bringing the metric back into play in order to examine how these things behave with respect to isometries, not with respect to projective symmetries, because on other locally symmetric spaces you do not have this luxury. So, okay, but anyway, this is the story for what happens on the sphere. So this part of the talk is due to myself and Thomas Leister. Okay, so it's actually very, very pleasant. What happens is that there's a lot of them which are trace-free. So these are just killing tensors which just happen to be trace-free. That's the dimension of the space.
Sorry, it's not sigma that's identically zero here.
Sorry? This is sigma. Sigma is the trace.
Oh. Okay.
So sigma with no indices is the trace of sigma with indices. Right? So the first thing is you could have a sigma which is trace-free. In other words, this trace is zero. Okay, there's a lot of those. Or the other possibility is that either sigma is a harmonic. Locally, this is not an overdetermined system, but on the whole sphere it is. So you start with a killing field in one little patch, and you notice it extends to the whole sphere. You look at the trace on the whole sphere, and then it turns out that sigma is a spherical harmonic with this particular eigenfunction and therefore this particular dimension. Or the other possibility is that sigma is constant, in which case then this is obliged to be just a constant multiple of the metric. So at some stage I probably should have pointed out earlier that an example of a killing two tensor is the metric itself, if you're starting with a metric and a metric connection and so on. And lo and behold, if you add all these numbers up, you get the right answer. All right, so this is how the killing tensors on the sphere break up. Killing two tensors on the sphere. All right, so all of that was sort of semi-classical. I mean, at least these dimension formulae go back to the 1980s to various people. What about complex projective space? Okay, so complex projective space is another very nice symmetrical Riemannian manifold. It's the next most symmetrical thing you can think of after the sphere.
So this is all with respect to the Fubini-Studi metric.
So this is the Fubini-Studi metric, as opposed to the round metric on the sphere. There's a whole class of spaces called locally symmetric spaces. And they include the sphere. And then the next most complicated thing is complex projective space. And here is what it is as a quotient of Lie groups, which is well set up with respect to the metric. Right. So the isometry group of complex projective space, complex projective n space, is SUm+1, and then this is the subgroup you have to mod out by if you're just standing at one point and looking at the isometries which respect that point. So the isotropy subgroup. Okay, but you know, I'm thinking of this as a Riemannian manifold. Right? So I'm not at the moment. I'm not taking the complex structure into account at all. This is the Fubini-Studi metric, but we're in the realm of Riemannian differential geometry. So, for example, the complex projective one space is the sphere, and I'm just thinking of this as the sphere, the round sphere. You can just ignore its complex structure. Right, what I'm about to now describe is a way of thinking of the sphere and figuring out what the, thinking of complex projective space and figuring out what the killing tensors are on complex projective space by some sort of geometric trick, right? But there's an alternative approach, and if you want to look at the alternative approach, you can look in this particular article. Okay, so here is the geometric trick which you can use in order to relate the Killing tensors on complex projective space to something a bit more familiar. All right, well, one thing is you can just fiber the sphere of an appropriate dimension by, you think of the sphere sitting inside complex projective space, you look at the complex numbers of unit modulus, U1, and have that act on the sphere, and the quotient is complex projective space. That's another way of saying that quotient up there. Okay, but when you do that, you can conveniently realize that the isometry group, which is SUM plus 1, there's some bigger groups lying around, but these bigger groups are acting on the sphere, or at least on the ambient space, Cm plus 1, rather than actually directly down on complex projective space. So the first thing that's acting is the m plus 1 by m plus 1 unit determinant matrices. Right? So they're certainly acting on Cm plus 1. Another thing that's acting is, well, because this is the sphere, just forget about the complex structure now and think of the sphere as sitting inside R 2n plus 2, then the other sort of obvious group that you have lying around is the isometries of that sphere. And by the way, before I go on, I should say that the metric that you have, the Riemannian metric on CP1, on CPn here, comes from just the round metric on the sphere. Right, so this is a Riemannian submersion, where you're looking at the round metric on the sphere. So here are isometries of the round metric on the sphere. And then one more thing that you have lying around here is that you can use this round metric and the complex structure here. You can lower one of the indices and say instead you have a skew form with in dimension 2n plus 2. Okay, so these three groups are somehow acting on this picture. And this is a familiar arrangement from sort of Kähler geometry, whereby any two of these groups intersect to give you SUm plus 1. Well, not almost. Okay, so you can take any two of these things and intersect them. So one way of thinking of the isometries down on CPn is that somehow when you lift them up to the sphere, they break into, well, you can think of them as having some sort of extra leeway in three different ways. Okay, and it turns out that this one's a really good one, this last one here, SPn plus 1R. Okay, so one of the things that you can do is think of this sphere, rather than being the round sphere, as being a homogeneous space for this particular group. So this group here is just the group of 2n plus 2 by 2n plus 2 matrices which are preserving a skew form, and it turns out that that acts transitively on the sphere. What you should do is, instead of thinking of the sphere as embedded, you should think of the sphere as being a space of rays emanating from the origin, and then this group acts. And the subgroup, which is preserving any particular base point that you like, I've called P. Right, now P stands for parabolic.
Because you see here the sphere, you're thinking of the group is acting on the sphere's contact transformations, right?
Oh yes. Yeah, that comes about here. Claude's ahead of the game as usual. So P here is a subgroup. It happens to be a parabolic subgroup, and what I'm about to describe is a very special case of a whole class of geometries called parabolic geometries, which include many familiar things like CR geometry and conformal geometry and so on. This is another one. And as Claude says, what we're doing here is thinking of the thinking of this sphere as having an extra structure on it, and these are the transformations which preserve that extra structure. The extra structure is that on the sphere, first of all, it's a contact manifold. So it's an odd-dimensional manifold. It has a codimension 1 maximally non-integrable distribution. So a codimension 1 submanifold of its subbundle of the tangent bundle. And these things are the these things, first of all, are these transformations preserve that structure, and they also actually, just because it's a subgroup of SLm plus 1, SL2m plus 2r, they preserve the great circles on this. These are both contact transformations and projective transformations. This contact distribution is very conveniently arranged because if you ask how does it sit with respect to this vibration, it's transverse to the vibration. So in particular, like the tangent space at CPN at any particular point, you can just uniquely lift that up and think of it as this, this codimension 1 distribution inside the tangent bundle of the sphere. Okay, so this contact structure is transverse to the vibration. Right, now as soon as you encounter these things, like, so it's a little bit similar to what we were doing before, the Dinkin diagrams become a little bit different. Right, so this is the Dinkin diagram for SP2n plus 2. It has n plus 1 nodes. Right, this is the Dinkin diagram at C n plus 1. Right, and this little cross at the front here is recording, in general, it's recording which particular parabolic subgroup you have. So this is part of some general theory.
Is the right way of thinking of the geometry of the sphere here, that not only do you have instead of, for a contact structure, you have a one form up to scale, but here you have a scale of one form.
Oh, no, it's one form up to scale. Up to scale.
That's for the contacts, right? But the transverse, I'm thinking about the preferred transverse rate vector field. It's not, but it's not scale.
No.
It's not.
No,
it's
no,
not
well, the scale up, right. So the scale is built in, right? Yeah. Just as it stands, just geometrically, there's no scale, but there are of course various bundles on here which are controlling your choice of scale. And the bundle is the bundle which is like corresponding to putting some weight over this node. Right? So it's like conformal weight or whatever. So yeah, so any sort of favorite construction like, you know, Reed vector fields and things like that is sort of built into the notation. But okay. Anyway, but let's not get carried away. So this is an example of a parabolic geometry. It's an example of a semi-simple Lie group. It's over the reals, but that's okay. Modulo some parabolic subgroup. Right, and when you have such a gadget, you have a class of invariant differential operators. Invariant means it's going to be invariant with respect to this group, this big group. You can pretty much list what all of the invariant differential operators are, and there's some of them are overdetermined in the sense of the previous slide, where the kernel will be finite dimensional. Okay, so again, at the risk of having some unexplained notation, there are these various bundles, like this bundle here, and differential operators, first order differential operator, which ends up in this bundle here. And as far as indices goes, in the contact directions you have k symmetric indices, and here, after having differentiated and so on, you take the k plus first gadget and you symmetrize over all of the indices. And just sort of by thinking about it, you might hope that this differential operator has something to do with the differential operator controlling killing fields on CPN. And indeed, this differential operator is covering this k tensor killing operator down on CPN. So if you're trying to solve this equation on CPN, you could look up on the sphere and see what happens. Right, and on the sphere, you get a finite dimensional space of solutions. Right, so this is your finite dimensional space of solutions. It's already given to you as an irreducible representation of the group, which is this symplectic group. And according to the standard hieroglyphics of Dinkin diagrams and what have you, and highest weights and all that, it's that one. Right? So this is a notation for a particular irreducible representation. But all of this is happening, by the way, all of this is happening on the sphere. It's not happening on complex projective space. You have to now figure out what happens if you try and look at solutions of this equation which descend to complex projective space. Right, so that's on the next slide. What happens if you try and push all this down onto complex projective space? Right, so one thing you can do is you can do some geometry intrinsically on complex projective space, which is what was in an article a long time ago with Jan Slovak of how you do this intrinsically on CPN, or intrinsically actually on any K manifold. Right? But just geometrically, once we've realized that there's this geometry going on, what you can do is take this representation of this group and just look at how it branches to an actual subgroup. The point is that, well, just on the level of Dinkin diagrams, Cn plus 1 is this Dinkin diagram for SP n plus 1, SP 2n plus 2, either over the reals or over the complexes, so you get a little bit confused at this point. And sitting inside that is another Lie algebra, which geometrically is just obtained by just sort of crossing out the last node here. So there's an AN Dinkin diagram sitting inside there, and which is actually, AN is actually the Lie algebra of SUN plus 1. And then there's a torus at the end, a simple scale thing, which has to do with this vibration, right? So you've got this action of U1, which is taking you from the sphere down to complex projective space. So just on the level of algebra and so on, you might suspect that this inclusion of this Lie algebra inside that Lie algebra is a good thing to look at with respect to trying to figure out which things happening on the sphere go down to complex projective space. All right, so lots and lots of hand waving here. Right, and you can either do this by theory, or you can actually do this by machinery. Once you've got to here, you can use some computer programming. You can use Lie. I'll just tell you, Lie is really good. So, yeah, I don't have a lot of time. What I can do, what I could do if I had a little bit more time, is you can just mechanize this process about branching from this Lie algebra to this Lie algebra. The reason I've even called this T1 here is that that's what Lie calls it. So an abelian Lie algebra of dimension 1 is called T1, like torus 1. And A7, this is the case when n equals 7. This is some matrix describing how the fundamental roots of one Lie algebra restrict to the other Lie algebra. So it's telling you how this is embedded inside C8. And then you can just ask Lie to perform this. I might do this at the end of the talk. If we've got time, I'll actually do this. And this is what happens. So, for example, what happens? So now you can do explicit numerical examples quite easily. So, for example, what about killing tensors on CP7? Okay, so you just run that previous program with k equals 3 and see what you get. And you'll get exactly 6 irreducible representations of SU8, on which U1 is acting trivially. So these are the things that you sort of expect to descend down to complex projective space. Right, now I'm just, going to boldly assert that that's what really happens, right? So for example, if you ask what is the dimension of the space of killing 3 tensors on CP7, again, you can ask Lee to compute the dimensions of these various spaces, whatever they are, and here are the dimensions, and then you add them up. That's what you get. That's the answer. And that's actually true. All right. Okay. So let me now spend a little time discussing what these dimensions actually turn out to be. All right, so we know that this is reasonably straightforward on the sphere, and you can ask, what do these dimensions look like on complex projective space instead? So let me just compare, like on one of these shopping sites where you're going to compare the sphere, advantages and disadvantages of the sphere versus complex projective space. All right. So, first of all, here's what's going on abstractly. So as I said, SUM plus 1 is this intersection of these two groups, and what you're really doing is looking at this particular representation and branching it. Geometrically, what that's doing is you're taking this irreducible representation, you're thinking of these as tensors in an appropriate dimension, and you're decomposing them under SLC. You're decomposing them under the complex structure, asking about how J acts. So these things here, which have 2K indices, break up into type, and you're looking at those which have type KK. Anyway, after a bit of stuffing around, you find, and the details are in this archive article, that this is dimension. All right, so at this point, you're either happy with this formula, that's really good, or you're unhappy because it's extremely complicated. I mean, it's not just that you're taking this horrible, quotient here, which is recognizable as being some other dimension of some irreducible thing, and you're actually squaring it and so on, and then you're adding all these things. Anyway, but this is, of course, something that you can just put onto Maple and experiment. Right, so now let's look at what's happening. So on the sphere, this is the comparison between the sphere and complex projective space. So this is when K is 1, you're looking at killing fields on the sphere, that was their dimension. We decided already that when K is 2, that's the dimension, and here is what happens when K is 3, K is 4, K is 5, and you can quite easily spot this pattern. Right, so I won't do it, but obviously you can, right? So there's some good formula going on here. What happens if you try and do exactly the same thing on CPN? Well, to start with, it looks okay, right? That's the dimension of SUM plus 1, n times n plus 1. Everything's real, by the way, here, right? So this is the real dimension of the real isometries of CPN. And even when you look at killing 2 tensors, it's actually quite a good formula. In fact, it's just sim2 of the previous space. So it's actually quite okay. When you look at K equals 3, it's not too bad. And when you look at K equals 4, you might even still hold out some glimmer of hope that there's some sort of pattern here. But I can't spot it. And in particular, if you go to K equals 5, I claim you get more serious polynomials. This is what happens when K is equal to 5. Right? So you get some ridiculous expression. And this is, of course, all done with computer algebra, with Maple and so on. And it's just, it just gets worse from then on. Right? So the sphere, all very nice, good pattern, complex projective space. I don't understand what's going on. But these are correct polynomials, so these are perfectly okay. Then you can ask about something a bit more experimental. So another way that you might assemble these dimensions is as what's called a Poincare series. Right? So what you can do is you can look at these dimensions and you can look at them as the coefficients of some infinite power series. Right? So T is just some formal parameter. I'm just looking at the dimension of, so K is, N is fixed, You're looking at killing tensors on CPN, and you're trying to assemble the dimensions into some sort of more sensible and compact form. So you can look at these dimensions and just look at this formal power series where these are the coefficients. And, you know, when n equals 1, we're just talking about the sphere. You expect there to be a nice formula, and there is. When on CP2, if you do it, actually, this often happens when you've got a Poincare series like this, which initially is a formal power series, actually turns out to be a rational function. Right? So this particular rational function, which happens for CP2, gives you all the dimensions of all the killing tensors, no matter what their valence, right? No matter what k is. This is really, really amazing. This is found by de Long in 1982 in a thesis at the University of Minnesota, and then he left mathematics. So, but his thesis is really good, and this formula is in there. This is what happens when k equals 3, and at this point I'm getting a bit more experimental because you can write down this power series and you can ask Maple to figure out, could this power series be a nice simple rational function? So you take the power series and you multiply it up by this, what the denominator is that you expect, and you see that you get, a fairly simple polynomial plus, well, if you go high enough, nothing. So you get these.
Actually, the first one for H2, you could simplify that further because the top is 1.
Oh, you can. Yes. Okay, you can simplify this one a little bit further, but not for the other ones. Okay, it's best to leave them like this, I think. So the denominator is going 3, 7, 11, 15. That's okay. These numbers on top are pretty nice numbers, aren't they? 1, 4, 10, 4, 1. 1, 9, 45, 65, and so on. Even this one. But this is all experimental, right? So it's just, plug all this into Maple and just. I was stuck in a room with COVID, being isolated after catching it at some conference in Banff, and so yeah. So anyway, so I was experimenting, and this is what appears experimentally to be true. And by appears, I mean you can check the first few thousand terms, right? It's obviously true. And but now Claude is trying to try to spot the pattern 116, 136, and so on and so on. So I'll just separate out what you have to now figure out. Okay, so this is a major challenge for the audience. Here are these just the numbers, right? These are the coefficients. I don't even know why it should be so symmetrical. But, you can spot there's something going on, like some perfect squares going down there, 1, 4, 9, 16, 25, and so on. And of course, if you've got a sequence of numbers like this, you can plug it into the online encyclopedia of integer sequences, and so on and so forth. And usually, the online encyclopedia of integer sequences will tell you what's going on here. But it doesn't. And I don't know what the next line. I mean, you can compute as many as you like, lines as you like. But I don't know what the pattern is, right? So this is mysterious. This is a plea for help. If you do the corresponding thing on the sphere, you get these numbers, right? So, and these are actually very, very standard, combinatorially nice numbers. They have a name. If you plug these into the online encyclopedia of integer sequences, you get a whole, 50 different realizations of what these numbers are. Right? So these are well understood. These other numbers, I don't know. Okay, so there's one. The only thing I can do is, again, being stuck with COVID and so on, and a computer, and the online encyclopedia of integer sequences. I'm now going to tell you experimentally how you can get these rational functions. All right. So I'll just run through this quickly. If you do it, you look at the Legendre polynomials. Here they are. you integrate these things in a slightly peculiar way to get these polynomials of odd degree. These are the Papulis polynomials. Here are the first few of them. And then I claim that actually, if you take this, this particular arrangement of polynomials, there they are, and you make this fractional linear transformation, then experimentally you get these Poincare series for the complex projective space. It's really weird. Okay. The other thing you can do is you can fix attention on two tensors. Let me just do that. Remember, on the sphere, there were 3 types. Here, there are 4 types on complex projective space. And again, they sort of break up into really, easy to understand things, like this is the trivial representation, multiples of the metric, and so on. I didn't really understand these until a couple of weeks ago, when Lane Houston pointed out an old article of his, whereby he's in a particular part of his construction is that if you start with a spherical, well, not a spherical harmonic, an eigenfunction of the Laplacian on the sphere on complex projective space, then if you take such a thing and you perform this operation, that gives you a killing field. Okay, and he has some quantum mechanical motivation for all that. Right, and now finally, here is the real puzzle that I don't understand at all. What's happening on quaternionic projective space? Okay, so that's another one of these nice, compact, locally symmetric spaces. Right, what's happening on quaternionic projective space? First of all, if you look at the 2 tensors, then Vladimir Matviev and Yuri Nikolaevsky, by some combination of geometry and algebra, but having nothing to do with what we've been discussing so far, have figured out that on quaternionic projective space, there are 5 types of these things. Right? So we have 3 types on the sphere, 2 types, and here 5 types. And here they are as abstract representations of the symmetry group. So it's that one. Okay, again, it corresponds to some eigenfunction of the Laplacian. This one, which I don't know how to interpret. This one, it's another eigenfunction of the Laplacian. Again, a bit mysterious. There's the trivial representation, and then there's one more. This is a really weird one. This here consists of killing tensors that you cannot get from killing vectors. Right, so these are sort of hidden symmetries. They're like what you get for the Kerr solution in general relativity, where there are killing 2 tensors which are not generated by killing fields. Right, there's a lot of these things, that's the dimension of them, and I don't know what's going on here either. I'll plead for help. The only thing is that there is a good relationship between quaternionic projective space and twistors. So I'll just run that by you, but again, it doesn't appear to help. Right? So here is quaternionic projective space as a homogeneous space in the usual way. Here is the complete analog of what you're doing in complex projective space. So you get a bigger sphere, and it's sitting inside quaternionic space. And this is, if you like, a standard twistor construction, which has a lot to do with Claude. And the various groups lying around. Here, like the direct analog of these groups that you have lying around for complex projective space. Again, you can intersect any 2 of these and so on and so forth. And you get some parabolic geometries, like the sphere here is a parabolic geometry. And so on. Right? So, so when you realize all this, there's a cause for rejoicing. It all seems to be just like complex projective space. Or you could even think of this complex projective space here as some other sort of parabolic geometry. So this is a parabolic geometry, goes by the name of C-contact projective geometry. So there are various sort of standard geometries lying around here. But, does this help? So there are two different parabolic geometries. Does this help? I've not been able to get it to help, even with Lee. Right? So you can just make guesses, wild guesses. You can ask Lee how various representations branch and so on. And you know, it's a mystery. Okay.
Okay, thank you. Questions?
Cool. So for this very special case of CP2 with the Fubini-Sudi metric, you could think of that as a self-dual manifold, and it has a very nice twistor space.
Yeah.
It would be good to reinterpret the Killing tensors as sections of appropriate holomorphic vector bundles on the twistor space.
Yes.
If you could sort that out, then that would be an extra hint as to what to do for quaternionic projective space, because presumably what you really want, it's a sort of different use of complex projective space. You're going to be looking at just holomorphic sections of some holomorphic bundle.
Yes,
that would be nice.
Yeah. Yeah.
That's got to be the flavor.
That has to be something to do. So definitely, if you're, for example, there are related questions which you can definitely approach that way. For example, what is the range of the killing operator just on fields, on vector fields? What is the range of the killing operator on these various homogeneous spaces? You want some sort of integrability conditions on the range. And yeah, if you do that on CP2, exactly what you say, you can figure out what the range is by holomorphic means.
But it's always an H0 question. It's not.
I know, yeah, yeah. Yeah.
So you're just trying to understand the kernel.
Yeah, yeah. I mean, that's right. That's right. This should be easier, if anything. Yeah. Just on CP2. Yeah. Yeah. I guess if I knew how to do CP3 rather than CP2.
Oh, yeah.
Okay, here's another question.
Yes, did I understand correctly that in order to find Killing tensors which are not expressed or built on vectors, you have to go to quaternionic?
Right, so, okay, right. Yeah, so just going back to this article of these two guys. Yeah, that's right. Yeah, so on a complex projective space, there are no hidden symmetries. There are no two tensors which aren't just obtained from killing vectors. All right? And here they found this explicitly. And also, the case that they also do explicitly is octonionic projective plane. Right? So that's the other one where you'd expect things to go wrong, and indeed they do. They analyse that in detail. And then they also maintain, well, I don't really understand why, they maintain that actually it's only the sphere and complex projective space where there are no hidden symmetries. On anything else, or I mean, once the dimension gets big enough, on any other locally symmetric space, there are indeed hidden symmetries.
So you mentioned octonions. There is a space.
Right.
Cayley plane.
Cayley plane. The Cayley plane. Yeah. That's the other sort of, really, really nice, homogeneous Riemannian manifold.
And do they do that in terms of the Riemannian submersion from the sphere? Or?
No. Okay. So yes. So what they do is that they work out So one of the ways of thinking of killing two tensors is conserve quantities along the geodesics. So in principle, if you know what the geodesics are, then you can figure out conversely what are the killing two tensors. So what they do is they write out some local coordinates on which you can figure out what the geodesics are, at least to a certain order. And that's enough to tell you what the killing two tensors are. That's their method. And they do it on the octonion, on the Cayley plane as well, that way.
Okay, I can probably more questions, but I can see that there's a countdown and we only have 36 seconds left. So let's have the rest of the questions with the coffee, which is being served now. Let's thank Mike for